Dark matter and dark energy are two of the deepest mysteries of modern cosmology. They are invisible and undetectable by conventional means, but their presence can be determined by their gravitational effects and their influence on the expansion of the universe. Together, they make up about 95% of the total mass and energy of the universe, with dark matter accounting for about 27% and dark energy for about 68%, and ordinary matter, everything we can see and interact with, making up only a small fraction. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it completely invisible to electromagnetic radiation and thus extremely difficult to detect directly. Its existence was first hypothesized in the 1930s by Swiss astronomer Fritz Zwicky. He observed that galaxies within clusters move at speeds that suggest the presence of much more mass than can be accounted for by visible matter alone. Since then, additional data from galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation have confirmed the existence of dark matter. Despite its invisibility, dark matter exerts a gravitational influence, affecting the structure and formation of galaxies and galaxy clusters. It acts as a cosmic framework around which visible matter accumulates and forms the large-scale structures observed in the universe. Dark energy, on the other hand, is the mysterious force that drives the accelerated expansion of the universe. The discovery of dark energy in the late 1990s came as a significant surprise to astronomers, who had expected that the expansion of the universe might be slowed by the gravitational pull of its contents. Instead, observations of distant supernovae have shown that galaxies are moving away from each other at an accelerating rate. Dark energy is believed to be a property of space itself, uniformly distributed throughout the universe and not diminishing as space expands. Its nature is even less understood than that of dark matter, and it poses a fundamental challenge to our understanding of the laws of physics because it does not fit into the standard model of particle physics or general relativity. Dark matter, which makes up about 27% of the universe, interacts with ordinary matter through gravity. It does not emit, absorb, or reflect light, making it invisible and detectable only through gravitational influence. The presence of dark matter can be inferred from its gravitational attraction to galaxies and galaxy clusters, affecting their rotation rate and distribution. This invisible matter acts as a cosmic framework, providing the gravity necessary for galaxies to form and cluster. In the early universe, the gravitational attraction of dark matter helped to amplify small inhomogeneities left by quantum fluctuations, leading to the formation of large-scale structures such as galaxies and galaxy clusters. These structures create potential wells within which ordinary matter can collect and cool, leading to star formation and the subsequent synthesis of heavier elements through nucleosynthesis in stars. Dark energy, on the other hand, makes up about 68% of the universe and is believed to be responsible for its accelerated expansion. Unlike dark matter, dark energy is not clustered but is uniformly distributed throughout space, exerting a repulsive force that counteracts gravity. The exact nature of dark energy remains one of the biggest mysteries in physics, but its effect on the expansion rate of the universe has critical implications for particle formation and cosmic evolution. Accelerated expansion affects the density and temperature of the universe over time, affecting the rate at which structures form and evolve. This expansion affects the cooling of the universe and the regions where particles can combine to form atoms, molecules, and eventually stars and galaxies. Supersymmetry, often abbreviated as SUSY, is a theoretical framework in particle physics that proposes a type of symmetry between two fundamental classes of particles: bosons, which carry forces, and fermions, which make up matter. According to supersymmetry, for every boson in the Standard Model, there is a corresponding fermionic partner, and vice versa. which has not yet been observed. These partner particles are known as superpartners, whose names repeat the names of their counterparts in the Standard Model, but with the addition of prefixes or suffixes, e.g., squarks are superpartners of quarks, and selectrons are superpartners of electrons. The appeal of supersymmetry is that it has the potential to resolve several unresolved issues within the Standard Model of particle physics and cosmology. One of the most important problems that supersymmetry aims to solve is the hierarchy problem associated with the huge difference in the strength of the gravitational force and other fundamental forces. Supersymmetry suggests that new symmetries in the laws of physics can stabilize the mass of the Higgs boson against quantum corrections that might otherwise make it much heavier, which provides a natural explanation for the weak weights and mass stability of the Higgs boson. Moreover, supersymmetry is the leading candidate for explaining dark matter, a mysterious substance that makes up about 27% of the universe but does not emit, absorb, or reflect light. Supersymmetric particles, especially the lightest supersymmetric particle, the LSP, are stable, electrically neutral, and weakly interact with each other, making them excellent candidates for dark matter. If these particles exist, they can explain the gravitational effects attributed to dark matter in galaxies and galaxy clusters. Despite the elegant theoretical rationale and the convincing solutions it offers for some of the most difficult questions in physics, no direct evidence for the existence of supersymmetry has yet been found. Particle gas pedals, such as the Large Hadron Collider, LHC, at CERN, are conducting extensive searches for superpartners of known particles. However, at the time of my last update, these efforts had not yet led to the discovery of supersymmetric particles, which has led to increased constraints on supersymmetric models, and pushed the predicted masses of superpartners to large values that are beyond the reach of current experiments. Are there theories suggesting that the particles are outside the Standard Model? There are several compelling theories suggesting the existence of particles other than those described in the Standard Model of particle physics. These theories attempt to address the limitations of the Standard Model and issues such as the nature of dark matter, the hierarchy problem, and the unification of forces. The best-known theories are supersymmetry, SUSY, string theory, and theories with extra dimensions. Supersymmetry, as mentioned earlier, extends the Standard Model by adding a superpartner to each particle, effectively doubling the size of the particle. These superpartners, which have not yet been observed, could help explain the mystery of dark matter and offer a solution to the hierarchy problem by stabilizing the mass of the Higgs boson. Supersymmetry predicts a number of new particles such as gluino, the superpartner of the gluon, and gravitino, the superpartner of the graviton, a hypothetical particle associated with gravity. String theory, another leading candidate for expanding our understanding of the fundamental constituents of the universe, proposes that elementary particles are not point-like points, but tiny vibrating strings. The vibrational modes of these strings correspond to different particles, and their vibrations determine the properties of the particles. String theory inherently incorporates supersymmetry and predicts the existence of many new particles, including those responsible for gravity, potentially offering a way to unify all fundamental forces. It also suggests that there are spatial dimensions in addition to the usual three. Theories of extra dimensions, such as those proposed in various formulations of string theory and approaches such as the brain world scenario, suggest that our universe may have more than just the three spatial dimensions we perceive. These extra dimensions may be packed and hidden at scales too small to be directly detectable with current experiments. Particles can propagate through these extra dimensions, which could explain why gravity is much weaker than other fundamental forces, and it assumes the existence of particles associated with these dimensions. Another approach involves grand unification theories, which seek to unify the electromagnetic, weak and strong nuclear forces into a single force by introducing additional symmetry groups. These theories predict the existence of new particles, such as heavy-gauge bosons, that may mediate transitions between quarks and leptons, turning one type of particle into another. While these theories are mathematically elegant and offer exciting solutions to standard model shortcomings, direct experimental evidence for the existence of particles outside the standard model remains elusive. Particle gas pedals, such as the Large Hadron Collider, are at the forefront of the search for these hypothesized particles. Their discovery would not only confirm these theories, but would fundamentally change our understanding of the fundamental structure and forces of the universe. Gravity, the weakest yet largest of the four fundamental forces, has a profound effect on particle formation, shaping the cosmos from the smallest scales to immense galactic structures. Although its influence is subtle in the field of particle physics, the role of gravity becomes more significant when we consider the broader context of the evolution of the universe and the formation of structures within it. The most direct effect of gravity on particle formation can be observed in star formation. When huge clouds of gas and dust in galaxies collapse under their own gravity, dense regions form within them, creating conditions favorable for nuclear fusion. The intense pressure and temperature in the cores of these nascent stars initiate the fusion of hydrogen atoms into helium, releasing energy in the process. This fusion, the heart of stellar nucleosynthesis, generates the heavier elements necessary for life and the diversity of chemical elements found throughout the universe. Gravity plays an important role in the formation of black holes, regions of space-time where the gravitational forces are so strong that nothing, not even light, can escape them. In extreme conditions near the event horizon of a black hole, theoretical processes such as Hawking radiation predict the creation of particle-antiparticle pairs from the very vacuum of space. While one particle falls into a black hole, another flies out, suggesting an exciting interaction between gravity and quantum mechanics that can influence particle formation. On a cosmological scale, the role of gravity in particle formation extends to the very structure of the universe. The distribution of matter, from the thread-like structures that make up the cosmic web to the formation of galaxies and galaxy clusters, is governed by gravitational attraction. This distribution, in turn, determines the regions where particles can clump together to form stars, planets, and other astronomical bodies. Although on small scales, the direct effect of gravity on the behavior of individual particles is overshadowed by the more powerful electromagnetic and nuclear forces, its cumulative effect on cosmic timescales and distances is crucial to understanding the evolution of the universe. The formation of particles, stars, and galaxies, and the very structure of the cosmos are all evidence for the fundamental role of gravity in shaping the universe from its earliest moments to the present day. Inflation theory is a key concept in cosmology that addresses some of the most fundamental questions about the early universe. Proposed in the early 1980s by physicists including Alan Guth and Andre Linder, inflation suggests that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion. This rapid expansion, far exceeding the speed of light, has increased the size of the universe by many orders of magnitude in the blink of an eye. Inflation was introduced to address several problems inherent in the Big Bang theory as it existed at the time. One of these is the horizon problem, which raises the question of how parts of the universe that are now widely separated could have been at the same temperature if light has not had time to travel between them since the universe's inception. Inflation explains that these regions were once close together and then were pushed apart by rapid expansion, allowing them to come to thermal equilibrium before they were separated beyond the horizon of causality. Another issue that inflation addresses is the flatness problem. Observations show that the universe is remarkably flat. That is, It conforms to the geometry described by Euclidean geometry on large scales, which requires fine-tuning of the initial conditions if the universe were to expand at a constant rate after the Big Bang. Inflation elegantly solves this problem by blurring any curvature in the fabric of the early universe. This causes the universe to appear flat on large scales, which is what is observed. Inflation also provides an explanation for the origin of the large-scale structure of the universe. The theory predicts that tiny quantum fluctuations in the early universe were stretched to astronomical scales by inflationary expansion. These fluctuations then served as seeds for the growth of structures in the universe, such as galaxies and galaxy clusters, through gravitational attraction. Inflation theory is supported by observations of the cosmic microwave background radiation, the afterglow of the Big Bang, in which small temperature fluctuations are observed, consistent with the predictions of inflation. These observations have cemented inflation as a cornerstone of our understanding of the early universe, even though this theory pushes the boundaries of modern physics. Although inflation theory has greatly expanded our understanding of the early moments of the cosmos, it also raises new questions, such as what caused inflation to begin and what stopped it. Various models of inflation have been proposed, some of which incorporate ideas from quantum field theory and string theory, in an attempt to provide a more complete picture of these dynamics. So how does inflation explain the uniformity of the cosmic microwave background? Inflationary theory offers a compelling explanation for the homogeneity observed in the cosmic microwave background, CMB, a weak afterglow of radiation that permeates the universe after the Big Bang. The CMB represents a nearly uniform temperature across the sky, with incredibly small variations, about 1 part in 100,000. This homogeneity, combined with isotropy, the sameness in all directions of the universe on large scales, presented a serious mystery to cosmologists before the advent of inflationary theory. Given the vastness of the universe and the finite speed of light, regions on opposite sides of the observable universe have not had enough time since the Big Bang to exchange heat or light and come to thermal equilibrium. This dilemma, known as the horizon problem, has raised questions about how the CMB can be so remarkably uniform. Inflation solves this puzzle by proposing a period of exponential expansion shortly after the Big Bang. According to inflationary theory, the observable universe expanded from tiny subatomic size to macroscopic size in less than a trillionth of a second. This rapid expansion means that regions now on opposite sides of the observable universe were once close together, within causal contact, before inflation separated them. These regions were able to come to thermal equilibrium by exchanging energy and smoothing out temperature differences before being stretched across the sky by inflation. Thus, when we look at the CMB, we see a snapshot of a much smaller homogeneous universe stretched across the vastness of space, which explains its uniform temperature. The small temperature fluctuations we observe in the MDB are explained by quantum fluctuations in the density of the universe that were present just before inflation. These fluctuations, once minuscule, were amplified by the inflationary expansion and spread to cosmic scales, forming the seeds of the large-scale structure of the universe, such as galaxies and galaxy clusters. The patterns of these fluctuations in the CMB have been accurately measured by experiments such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, providing strong support for the inflationary model. Antimatter is a fundamental concept in physics that mirrors the properties of matter, but with opposite charges. For every type of particle that makes up matter, there is a corresponding antiparticle that makes up antimatter. These antiparticles have the same mass as their matter counterparts, but have opposite electric charge and different quantum numbers. The most famous examples are the positron, the antiparticle of the electron, the antiproton, which carries a positive charge, and the antiproton, which has the same mass as the proton but a negative charge. The existence of antimatter was first predicted by British physicist Paul Dirac in 1928, based on his work on expanding the equations of quantum mechanics to take into account the theory of special relativity. Dirac's equations assumed the existence of particles that have the same mass as electrons but opposite charge. This prediction was confirmed in 1932 when Carl Anderson discovered the positron. This discovery was revolutionary because it provided the first evidence for the existence of antimatter and confirmed Dirac's theoretical framework. When a particle of matter collides with an equivalent antiparticle, they annihilate each other in an energy explosion, usually producing gamma rays. This annihilation process shows the equivalence of mass and energy described by Einstein's MPMC quadratic equation, and is an integral part of the interaction between antimatter and matter. Antimatter is not just a theoretical curiosity, it has practical applications and significance. In medicine, for example, positron emission tomography, PET, is based on the detection of gamma rays from positron annihilation to create detailed images of the body. In addition, understanding antimatter is crucial to advancing our knowledge of the universe. Cosmologists study antimatter to answer fundamental questions about the Big Bang and why the observable universe is composed almost entirely of matter. Despite theories predicting that equal amounts of matter and antimatter formed in the early moments of the universe. The study of antimatter is also pushing the boundaries of particle physics by challenging scientists to create, capture, and study antiparticles in the laboratory. For example, experiments with antihydrogen atoms aim to compare the properties of hydrogen and antihydrogen to test the fundamental symmetries of nature. This research could open up new physics beyond the standard model, providing insight into the forces and particles that shape our universe. Now let's talk a bit about the CP violation and how it relates to the matter-antimatter asymmetry. CP violation refers to a fundamental phenomenon in elementary particle physics, where the interaction of charge conjugation C and parity inversion P is not conserved. Simplistically, this means that the processes of transformation of some particles into corresponding antiparticles proceed differently when charges and spatial orientation are changed. CP violation is very important for understanding the matter-antimatter asymmetry in the universe. In the early universe, matter and antimatter were produced in nearly equal amounts during particle-antiparticle creation processes. However, if all physical processes perfectly observed CP symmetry, matter and antimatter would completely annihilate each other, leaving behind a universe devoid of matter. The observed asymmetry of matter and antimatter suggests that there must exist processes in which CP symmetry is broken, favoring the production of matter over antimatter. This violation of CP symmetry allows for subtle differences in the behavior of particles and antiparticles, resulting in a small excess of matter that ultimately produce the structures we see in the universe today. CP violation has been experimentally observed in some rare elementary particle decays such as neutral kaons and B mesons. These experiments have provided insight into the mechanisms responsible for creating the matter-antimatter asymmetry in the early universe. However, the exact cause of CP violation and its relation to the observed matter-antimatter asymmetry are still active areas of research in particle physics. Do we really understand the origin of the universe? This question has puzzled scientists, philosophers, and theologians for centuries. Delving deeper into the depths of cosmology and elementary particle physics, we find glimpses of the cosmic drama that unfolded billions of years ago. Despite our best efforts, the final birth of the cosmos is shrouded in mystery. Theories like the Big Bang provide a framework for understanding the evolution of the universe from the earliest moments of its existence. But when we look at the moment of creation, we encounter a realm where the laws of physics are broken and our common understanding crumbles. It is a realm of extreme temperatures, densities, and energies where profound changes are taking place in the fabric of space-time. In our quest to understand the origins of the universe, we face the limitations of human knowledge and scientific research. Can we ever hope to unravel the mysteries of existence with our limited intellect and empirical methods? Are there areas of knowledge beyond human understanding? Some argue that the desire to understand is an inherent part of human nature that drives us to explore, ask questions, and seek answers to the deepest mysteries of existence. Others argue that there is a limit to what we can know, and that some aspects of reality may forever remain beyond our comprehension. How does the concept of something fit into modern physics? This question challenges our fundamental understanding of reality. From the perspective of modern physics, nothingness is simply the absence of matter or energy. On the contrary, it is a complex and dynamic landscape governed by the laws of quantum mechanics. In quantum physics, the cosmic vacuum is far from nothing. It is full of virtual particles that appear and disappear spontaneously, borrowing energy from the void for a moment before annihilating each other. This phenomenon, known as vacuum fluctuations, indicates that even in the absence of particles, the fabric of space-time is buzzing with activity. Moreover, the concept of nothingness is intertwined with the mysteries of the origin of the universe. The Big Bang theory posits that the universe emerged from a singularity, a point of infinite density and temperature. But what preceded the Big Bang? Did anything actually exist before the expansion of the universe? Or are there dimensions of existence beyond our current understanding? Research in particle physics has far-reaching implications that go beyond laboratory studies and have many benefits for society. While the topic may seem esoteric, advances in particle physics are producing tangible results that affect our daily lives. One of the important contributions of particle physics research is its role in medical imaging and therapy. Technologies such as PT, positron emission tomography, and MRI, magnetic resonance imaging, have emerged from the study of particle physics. These imaging techniques are critical to the diagnosis and treatment of disease, improving the health of millions of people around the world. In addition, particle physics has paved the way for improved radiation therapy in the treatment of cancer. Techniques such as proton therapy, which uses beams of protons to precisely target tumors with minimal damage to surrounding healthy tissue, have emerged from particle physics research. These techniques offer more effective and less invasive treatment options for cancer patients. Research in particle physics has contributed to the development of innovative materials and technologies. For example, the World Wide Web, invented at CERN to facilitate communication between researchers, has changed the way information is accessed and shared globally. In addition, advances in particle detector technology have led to more sensitive detectors used for safety testing, environmental monitoring, and even archaeological research. The search for fundamental knowledge in particle physics often stimulates progress in other fields as well. Collaborations among physicists, engineers, and mathematicians foster interdisciplinary research that promotes innovation in many different fields. Future discoveries in particle physics promise to change many aspects of our daily lives. While some of these advances may seem distant or abstract, their potential impact on society can be profound. One area where future discoveries could have a significant impact is energy production and storage. Breakthroughs in particle physics can lead to the development of more efficient and sustainable energy sources, helping to address pressing issues such as climate change and energy security. For example, advances in fusion energy, inspired by the study of plasma physics in particle gas petals, may one day provide a clean and virtually limitless source of energy. Discoveries in particle physics can lead to advances in technology and computing. The development of quantum computing, which relies heavily on the principles of quantum mechanics studied in particle physics, could revolutionize fields such as cryptography, drug discovery, and artificial intelligence. Quantum computers can solve complex problems exponentially faster than classical computers, opening up new opportunities for scientific research and innovation. While the study of particle physics offers great potential for scientific progress, it also raises a number of ethical considerations that require careful consideration. One such aspect is resource allocation. Particle physics experiments often require significant financial investment and access to advanced technology. Critics argue that these resources could be used to solve pressing social problems such as poverty, health, and education. Proponents of quantum computing, however, argue that investments in basic research can lead to unexpected technological breakthroughs and long-term social benefits. Another ethical concern is the safety of particle physics experiments, especially those involving high-energy particle gas pedals. While the likelihood of catastrophic events resulting from these experiments is extremely low, some worry about potential risks, such as the creation of micro-black holes or the release of dangerous radiation. Researchers and regulators must carefully assess and mitigate these risks to ensure the safety of both experimental participants and the public. There are ethical considerations associated with the dissemination of knowledge and the potential misuse of scientific discoveries. Particle physics research often provides valuable insights into the fundamental workings of the universe, which can have broad implications for technology, medicine, and other fields. However, there is a risk that this knowledge could be weaponized or used for harmful purposes. Scientists and policymakers must consider how to balance the benefits of scientific progress with the need to prevent misuse and ensure responsible knowledge management. In addition, there are ethical issues associated with international collaboration and dissemination of particle physics research. Collaborative efforts between scientists from different countries are essential to advance knowledge in this area. However, issues such as intellectual property rights, data sharing, and fair access to research opportunities can arise, especially where resources are limited or there are differences between countries. Ensuring honest and transparent collaboration is essential to upholding the principles of scientific integrity and promoting global progress. While particle physics research holds tremendous promise for scientific discovery and technological innovation, it also presents complex ethical challenges that must be addressed thoughtfully and responsibly. With these ethical considerations in mind, and with an open dialogue, scientists, policymakers, and society at large can work together to overcome the ethical challenges of particle physics research and maximize the benefits to humanity. As we conclude our journey in reflecting on the emergence of particles from seemingly nothingness, we are confronted with profound philosophical questions that go beyond empirical science. Perhaps in the cosmic symphony of creation lies a deeper truth beyond our current understanding, a truth that speaks to the interconnectedness of all things and the infinite potential embedded in the fabric of reality. Could it be that particles emerge not from the void, but from the limitless reservoir of possibilities that permeates the cosmos? Ultimately, the question of how particles form from nothing forces us to consider our place in the vastness of the universe and to embrace the wonder and mystery that surrounds us. This challenges us to expand our consciousness beyond conventional thinking and embrace the limitless possibilities underlying existence. How do you think particles came into being? How did it all begin? Share your thoughts in the comments below. Thank you for watching.